Well, hello once again. In the last class, we talked about Raoult's law for volatile and non-volatile solutes. In today's class, we'll be talking about ideal and non-ideal solutions. We'll see what does ideal and non-ideal solutions means. We generally say that a solution which obeys Raoult's law is an ideal solution, and a solution which does not obey Raoult's law is a non-ideal solution. Here I tell you means why it happens that solutions sometimes they seems to obey Raoult's law, while in sometimes we can say that they are not obeying Raoult's law. Suppose I have prepared a solution, and that solution is prepared by mixing a solvent, say A2, with a solute, say B2, and together they are giving me a solution, say AB. So I can say I will get 2 moles of AB. Here I will see that there is a bond between A and A. Likewise, there is a bond between B and B, and there will be a bond between A and B. If the bond strength between A and BB is nearly equal, and that is nearly equal to that between A and B, such a solution is said to be an ideal solution. In such a solution, what will happen? Since the bond strength is nearly same, there is no more attraction or less attraction. In that case, delta H of mixing, we can say delta H of mixing is 0, and delta V of mixing is also 0. So an ideal solution is that which obeys Raoult's law. For such a solution, the attraction between solute-solute molecule, solvent-solvent molecule is nearly same that between solute and solvent molecule. So neither the attraction is more nor the attraction is lesser. Had the attraction been more, the solute and solvent particles would have come closer. In that case, there would have been a decrease in the volume, and we couldn't have said that there is no change in the volume. Likewise, in case the attraction would have been stronger, the energy of the solution would have decreased, and large amount of energy would have given out. In that case, the solution would have become exothermic. This process of solvation would have become exothermic. In that case, delta H would also have become negative. But for an ideal solution, neither the attraction is stronger nor the attraction is weaker. That's why neither there is an increase nor there is a decrease in the volume. Likewise, neither the process is exothermic or endothermic. So as far the sign of delta H is concerned, neither it is negative nor it is positive. If I talk about this is an ideal solution. So here is the example of an ideal solution. This is an ideal solution. Now if I talk about a non-ideal solution. Now in that case, say the attraction between AA is nearly equal to that between BB, but the attraction between AB is not equal to that. Such a solution is a non-ideal solution. So 2 conditions they are possible in such a solution. Either the attraction can be stronger or the attraction can be lesser. I'll give you one example for that. Randomly I am taking some value. Suppose the attraction between AA is 3.5. The attraction between BB is 3.4. And the attraction between AB is say 4.5. That means the attraction is stronger. If the attraction is stronger, the solute and solvent molecule, they will come closer. When they will come closer, there will be a decrease in the volume. So we can say that delta V of mixing is less than 0. That means negative. Likewise, when solute and solvent they are coming closer, they are experiencing more attraction. And due to larger attraction, their energy is decreasing. So large amount of energy will be given out. The process will become exothermic. In that case, delta H of mixing is also negative. Such a solution is said to show negative deviation from Raoult's law. Likewise, again, we are taking another example. Say the attraction between solvent-solvent particle again is 3.5. That between solute-solute particle is 3.4. But the attraction between solute and solvent particle is say 1.5. That is much weaker than between solute-solute and solvent-solvent particle. In such a case, solute and solvent particle, they will move away from each other. when they'll move away from each other, they will experience some repulsive forces. That means there will be an increase in the volume. So in that case, we can say delta V of mixing is more than 0. Now when they are experiencing repulsion and they are moving away from each other, that means the energy of the system is increasing. So it will absorb energy from the external source. In that case, it will become endothermic, and delta H of mixing will also be more than 0. That is positive, volume increase is positive, and delta H sign is also positive. Such a solution is said to show positive deviation. So as far non-ideal solutions are concerned, we have two different type of non-ideal solution, that is those showing positive deviation and negative deviation. For them, I will show you their vapor pressure composition diagram. Here we can see this one is a vapor pressure composition diagram for a positive deviation. In this you can see that the expected value of the vapor pressure could have been this. For solution, this could have been the expected vapor pressure. But the actual vapor pressure is more than that, that is this. So since there is no attraction, or we can say since there is a weaker attraction between the solute and solvent, they will have prominent tendency of moving into the vapor phase. That's why the vapor pressure will be more than that expected. So this is for the positive deviation. Next we'll see for negative deviation. In this you can see that the green line shows the expected vapor pressure, but here the red line is showing the actual vapor pressure. That means the pressure which we were expecting, the pressure is found to be much lesser than that, because there is a prominent attraction between the solute and solvent particles. So they will have little tendency of moving into the vapor phase, and that's why they will exert lesser vapor pressure than expected. So this is the vapor pressure composition diagram for positive deviation and negative deviation. Well, here in this case, I would like to show you some examples of ideal solution. For ideal solution, you can see it can be a solution of benzene and toluene, N-hexane and heptane, chlorobenzene and bromobenzene. Well, again, we'll move on to our topic, that is, by now the topic which I was explaining you, that is ideal and non-ideal solution. We are moving back to that. That is, a solution which obeys Raoult's law is said to be an ideal solution, whereas a solution which does not obey Raoult's law is a non-ideal solution. And as for non-ideal solutions are concerned, they are further classified into two parts, that is solution showing positive deviation and solution showing negative deviation. Well, the next topic which we had to do is the colligative properties. So we'll see what does colligative properties means. Colligative properties. As far colligative properties are concerned, these are the properties which depends upon the number of solute particles in the solution, that is on the concentration of the solution. The properties which depends on the concentration of the solution are said to be colligative properties. Such properties that does not depend on the nature of the particle. I give you one example for that. See, as far the boiling point of water is concerned, the boiling point of pure water is 100 degrees Celsius. If I add some sodium chloride into that, the boiling point will get elevated. How much will be the elevation in the boiling point? That basically depends upon the amount of salt I am adding. The more the amount of salt I will add, the higher will be the elevation in the boiling point. That means elevation in boiling point is a colligative property. It is basically depending upon the quantity of the salt, and it is not depending on the type of salt. So colligative properties, we can say colligative properties, they are directly proportional to the number of solute particles. They are directly proportional to the number of solute particles. And colligative properties, they are also inversely proportional. Colligative properties, they are inversely proportional to the molar mass of the compound. So higher the molar mass, lesser will be the colligative property. And we basically use all these colligative properties to calculate the molar mass of an unknown solute. This is the main utility of all these colligative properties. So colligative properties, they are used to calculate the molar mass of an unknown solute. We have 4 different types of colligative properties. The first one is relative lowering in vapor pressure, which we have already done in Raoult's law. Second is elevation in boiling point, which we'll do. Third one is depression in freezing point. And the last one, that is fourth one, is osmotic pressure. Osmotic pressure. Well, just to recapitulate, I would like to show you this relative lowering in the vapor pressure. Relative lowering in the vapor pressure we have done here in the Raoult's law for non-volatile solute. And we know that this term is relative lowering in the vapor pressure, and it is equal to the mole fraction of the solute, as you can see in this formula. So relative lowering in the vapor pressure again is a colligative property. The more the amount of salt you will add, the lesser will be the tendency of the solvent to move into the vapor phase, and hence there will be a decrease. We can say the more will be the decrease in the vapor pressure. Hence relative lowering is equal to the mole fraction of the solute in the solution. Now we'll move on to the second colligative property, that is elevation in the boiling point. Elevation in boiling point. Well, before starting with that, we'll see what does a boiling point means. Boiling point is a temperature at which the vapor pressure of a liquid becomes equal to atmospheric pressure. So boiling point is a temperature at which the vapor pressure of a liquid becomes equal to atmospheric pressure. As you will heat a liquid, more and more particles will move into the vapor phase. Its pressure will increase and ultimately it will become equal to the atmospheric pressure. It will not cross that value because it's an open container. So maximum value that the vapor pressure of a liquid can have is equal to the atmospheric pressure. Suppose I have got water at say 40 degrees Celsius. If I am heating it, its vapor pressure will increase and ultimately it will become equal to atmospheric pressure, and that is at 100 degree at sea level. So we say that boiling point of water is 100 degree at sea level. But suppose I add a non-volatile solute in water. As I explained you earlier, a non-volatile solute will reduce the vapor pressure. It will reduce the vapor pressure of a liquid. That means lesser number of particles are moving into the vapor phase. That means now it will not become easier for a liquid or the vapors of a liquid to become equal to atmospheric pressure. That means I have to heat it more. So we'll see some elevation in the boiling point. So I'll give you one example. Say at room temperature, pure water has got a vapor pressure of say 500 millimeters. If I heat it, it will become equal to 760 millimeters at 100 degree. Now if I add some sodium chloride into that, this 500 millimeters will decrease. Say it has become 300. Now at 100 degrees Celsius again, it is not equal to 760, it is lesser than that. That means when I have added some sodium chloride into water, its vapor pressure has decreased. And at 100 degree it is not equal to atmospheric pressure. That means now 100 degree is not the boiling point of that solution. It is way ahead of that. I had to keep on heating, And the boiling point of liquid now will be more than 100. It can be 101, 102, 110, 120, anything. That basically depends on the quantity of salt I am adding. The more the amount of salt I will add, the higher will be the elevation in the boiling point. So that means more the amount of salt I will add, the more the amount of salt I will add, the lesser will be the vapor pressure, and hence higher will be the boiling point. So this is elevation in boiling point. Now we'll see it graphically how it happens. Suppose here I am showing you a graph, and this graph is between vapor pressure and temperature. Suppose this is 1 atmospheric pressure. Here the value is 1 atm or 760 millimeters. 760 millimeters of mercury. This is the atmospheric pressure. At any temperature, say this is T degree Celsius, at this temperature I have got pure water. Now you know pure water is more volatile, so it will have a higher vapor pressure. So let me mark it as pure water. And if I add some sodium chloride into that, its vapor pressure will decrease. At the same temperature, the vapor pressure of the solution will be this. I am marking it as water plus sodium chloride. So at same temperature, water will have higher vapor pressure as compared to water plus sodium chloride. Now if I start heating them, their vapor pressure will increase. For water, we will see the increase will be like this, and it will become equal to atmospheric pressure. Somewhere here, this line here at temperature excess is representing the boiling point of pure water. Say this temperature is T1. Likewise, if I heat water plus NaCl, its vapor pressure will also increase and will become equal to atmospheric pressure at this temperature. Say this temperature is T2. So from here you can see that there is an elevation in the boiling point. Suppose T1 is 100 degrees Celsius. So T2 is anything more than 100 degrees Celsius. There is an increase in the boiling point, elevation in the boiling point. This difference is known as elevation in the boiling point. Elevation in boiling point is represented by delta TB, and that is equal to T2 minus T1. We say that elevation in boiling point is directly proportional to concentration, because the more the amount of salt you will add, the lesser will be the vapor pressure like this, and hence there will be more elevation in the boiling point. More the amount of salt I am adding, lesser will be the vapor pressure, higher will be the boiling point. So there will be an elevation which is directly proportional to the concentration. Now since there is a large change in the temperature, we choose a concentration expression which does not change with change in temperature. That is molality. So I can say delta TB is directly proportional to molality. Or I can say delta TB is equal to Kb into molality, where Kb is known as molal elevation constant, also known as ebuloscopic constant. And you have to remember the value of Kb for water, which is 0.52. Now if we expand this formula, because we know the formula of molality, we can write delta TB is equal to Kb into weight of solute upon molar mass of solute into 1000 upon weight of solvent. As I told you earlier, the main utility of colligative properties is to calculate the molar mass of an unknown solute. So this formula can be used for calculating the molar mass of an unknown solute. What I can do, I can write Mb is equal to Kb into Wb into 1000 upon delta TB into WA. This is what I can write, and this is how I can express. So this formula can be used for calculating the molar mass of an unknown solute through elevation in boiling point. So this is what elevation in boiling point is all about. Next colligative property, third colligative property, that is depression in freezing point. So third colligative property is depression in freezing point. Again, before starting with that, we'll see what freezing point basically means. Freezing point is a temperature at which the vapor pressure of the solid and the liquid state of a substance becomes same. So it is a temperature at which the vapor pressure of the solid and the liquid state of a substance becomes same. That is, if I take an example of water, at 0 degree, the vapor pressure of water and ice is same. So that is the freezing point of water. Well, as for freezing and melting point, they are concerned, they are all the way same, but we generally use different definitions for that. If someone asks what is a freezing point, it's a temperature at which the vapor pressure of the solid and the liquid state of a substance is same. And if someone asks what's a melting point, it's a temperature at which the solid and the liquid state of a substance can exist at equilibrium or in equilibrium. For example, if I talk about water, at 0 degree I can have water and I can have ice also. Both of them, they can exist at 0 degree. From 0 degree, if you start decreasing the temperature, the water will start getting converted to the ice. If you start increasing the temperature, the ice will start getting converted to water. But at 0 degree, both of them, they can exist together. So that's the definition of the melting point. Now we'll see what happens when a non-volatile solute is added to a solvent. When a non-volatile solute is added to a solvent, its vapor pressure will decrease. As I explained you this thing in relative lowering in the vapor pressure and also elevation in boiling point. When the vapor pressure will decrease, it means the vapor pressure of the liquid will not be equal to its solid state at the earlier temperature. For example, at 0 degree Celsius, the vapor pressure of water was equal to that of ice. But now when I have added some non-volatile solute, its vapor pressure will be lesser than that of ice. So it will not freeze at 0 degree. It will be much lesser than 0 degree. It can be -1, -2, -3, anything like that. I'll explain you that graphically. We'll see how it decreases. Now suppose, again, same type of a graph. This line is expressing this. On this axis, I am representing vapor pressure, and on this axis, I am representing temperature. Vapor pressure and temperature. Again, here I have got a pressure. This pressure is not 1 atmospheric pressure like elevation in boiling point. We are not taking it hard and fast as 1 atmosphere. It has got any value. Say it is X atmospheres. At this temperature, I've got pure water. At this means I've got a sample of water which has got this pressure. So here I'm showing this is the sample of water which has got this pressure. This is the sample of water which has got this pressure. Now if I add, say this is the vapor pressure of pure water. If I add some sodium chloride into that, its vapor pressure will decrease. But if I'm saying that both of them, they have got the same vapor pressure, that means water plus sodium chloride is at higher temperature. I have heated water plus NaCl. That's why the vapor pressure has increased and ultimately it has become equal to that of pure water. So on this axis, this is any pressure, X atmosphere. I have got pure water which has got this pressure, and I have got water plus NaCl which again has got this pressure. That means water plus NaCl will be at higher temperature. So this point is representing pure water, whereas this point is representing water plus NaCl. If water and water plus NaCl, they both have got the same pressure, vapor pressure, that means water plus NaCl is at higher temperature. Now here at any temperature, this is the temperature I have got. Here at any temperature, let it be minus 10 degrees Celsius, I have got a sample of ice. This is a sample of ice I have got at this temperature. Now what I am doing, I am heating this sample of ice from minus 10. When I will start heating this sample of ice, its vapor pressure will start increasing. Now suppose here somewhere this point is representing a temperature of say 0 degrees Celsius. Say this temperature is 0 degree Celsius, or I can say this is temperature T1. When I'll heat ice, its vapor pressure will increase and will become equal to this point at 0 degrees Celsius. So this curve is showing ice. Again, I'm recapitulating it. Say this temperature is minus 10 degrees Celsius. At that I have got a sample of ice. I'm heating ice, its vapor pressure is increasing. At 0 degrees Celsius, this is the vapor pressure of ice. On the other hand, what I am doing, I am decreasing the temperature of sample of water. So its vapor pressure will decrease, because with decrease in temperature, the evaporation decreases, and with increase in temperature, the evaporation increases. So if I decrease temperature, the vapor pressure of water will decrease, and it will become equal to that of ice at 0 degree. So this line is representing water in the liquid state. So you can see that at 0 degrees Celsius, the vapor pressure of water and ice is same. So 0 degree is the freezing point of pure water. Now what about water plus NaCl? If I start cooling it, its vapor pressure will also decrease. But you will see that at 0 degrees Celsius, it is not equal to that of ice. It is much lesser than that. Further, if I cool it, it will become equal to that of ice at this temperature. This is the temperature at which it is becoming equal to that of ice. This temperature, I am representing it by temperature T2. So you will notice there is a decrease in the temperature. Pure water is freezing at 0 degree, but water plus NaCl is freezing at a much lower temperature than 0 degree. This is depression in freezing point. So here we can say depression in freezing point, that is equal to T1 minus T2. This difference is known as depression in freezing point. Now again, depression in freezing point, since it's a colligative property, depression in freezing point is directly proportional to concentration. The more the amount of salt I will add, the lesser will be the vapor pressure. Hence it will take much lower temperature to become equal to that of ice. Again, since there is a decrease in temperature, since there is a change in temperature, the concentration will be expressed in terms of molality. So delta TF is proportional to molality, or I can say delta TF is equal to Kf into molality, where Kf is known as molal depression constant or cryoscopic constant. You have to remember that its value for water is fixed, that is 1.86. This is the value of Kf for water. If we write this formula in the expanded form, we can write delta TF is equal to Kf into weight of solute upon molar mass of solute into 1000 upon weight of solvent. So what I can write, because this colligative property is used for calculating the molar mass of an unknown solute, I can say that molar mass of solute is equal to Kf into weight of solute into 1000 upon delta TF into WA. So this formula can be used for calculating the molar mass of an unknown solute through depression in freezing point. A question in your textbook is given based on this, where it has been stated that two elements A and B, they combine together to form two different type of compounds, that is EB2 and EB4. When 1 gram of each is dissolved in 20 grams of benzene, the depression in freezing point is found to be 1.3 and 2.3 Kelvin. If the Kf for benzene is 4.9, what are the atomic mass of A and B? So in such type of question, what you can do, you can calculate two different molar mass, like you can calculate the molar mass of AB4 and you can calculate the molar mass of AB2 through this formula. The difference of these two molar masses will give you 2 into atomic mass of B, twice of atomic mass of B. So if you divide this 2B by 2, you will get atomic mass of B. And if you put that atomic mass of B in any of these two values, you can easily calculate the atomic mass of A. So this is what you can do in that. So in this session, we have done some colligative properties like relative lowering in the vapor pressure, elevation in boiling point, and depression in freezing point. Next session will be the last session. In that, we'll be doing osmotic pressure and abnormal molar mass. In that, we'll be basically doing the Van 't Hoff factor, the degree of dissociation and degree of association for electrolytic solutes. Thank you.